All right, thank you. You are very welcome to download whatever you wish during my lecture. I won't be offended at all. Not that you needed my permission. All right, we're going to switch gears a little bit from mantle isotopes and move into the world of active source seismology, which for all of its benefits may not be able to show us where EM1 is and what it is, but it does have many uses, as I hope you'll see. So I hope you had a lot of coffee at the break, because I want to show you a lot of stuff that I think we can learn about subduction zones using this type of seismology. All right, so I think that Doug and Brandon have given you great introductions to general principles about seismology and told you about the wide spectrum of passive seismic imaging techniques that are out there. And so today I'm going to focus on active source seismology. And the thing that really makes this special is that not only do we control where we put our receivers for sound waves, but we can also control our source, how big it is, where it is, when it is. And so this means that we have sort of a unique ability to do a higher resolution of imaging of the Earth than is possible with some other types of methods. And so, and we can really optimize depending on what we want to see. And so I have my terrible cartoon up here of a marine experiment where we're creating sound waves with an air gun source, and we can record those on streamers or on other autonomous seismometers. So we'll talk more about that. But just to kind of whet your appetite for the kind of constraints we can have, we can look at the Earth in kind of this kind of detail. So, I didn't put a scale bar here, but this is about 1 kilometer, and this plot is shown at a vertical exaggeration of 2 to 1. But you can see detailed sedimentary layering, thrust faults, and other structures. And we can also get really detailed constraints on seismic wave speeds in the Earth. And so that's being shown here with the colors behind this image, where reds and warm colors are slower, and blues are faster. But hopefully you can see there's like a nice low velocity zone here within this area along the subducting plate boundary. So we'll talk about all of this in more detail. So we're capable of doing this really detailed and high resolution imaging, and that's really, but we are limited in terms of how deep we can see and the kind of spatial areas we can cover. This is necessarily a pretty focused and detailed approach, so it's strongly complementary to other kinds of seismic imaging, but because of the scale lengths is also very complementary to drilling and geology and many other things. So hopefully you'll be convinced about all that. All right, so there's sort of 2 broad kinds of active source imaging that we do, and there's many overlaps here, but we can, just for these purposes, there's seismic reflection data. These are, so here we're looking kind of across the bending area of a plate entering the trench and kind of in depth, which is in 2A travel time. And hopefully you can see the seafloor, lots of sediments. They're being offset by different faults. We have this feature here, which is the moho. And so these data are really good at giving us detailed pictures of faults, sediments, magma chambers, and other structures that have a contrast in velocity and density and kind of create a reflection like this. And these are complemented by wide-angle reflection-refraction data, which are normally used to create models of P-wave velocity of the Earth. And so this reflection image is from here, and so now we're looking in depth across the incoming plate. This is colored by P-wave velocity. So all the oranges and yellows are crust. I've changed up the color scale on you. The blues and greens are sediments and water, and then kind of the reds and purples are the upper mantle. And so we can use these sound speed changes to infer changes in composition and things like that. Of course, you can look at reflective boundaries in these and get velocities from these, but these are kind of the 2 broad categories. So I'll apologize in advance. I'm going to show you a lot of pictures from Alaska because it's my talk, and I love Alaska. It's my favorite subduction zone. But I'll try and have a little diversity and bring in some other subduction zones too. Okay, so before I talk in a little more detail about these 2 different kinds of seismology, I just want to give you the list of why it's useful to even know anything about these kinds of methods. And basically, they can do a bunch of stuff for us. We can learn a lot about subduction zones using these data. We can have constraints on the overall architecture of the subduction zone, both along the megathrust and beneath the arc to depths of 50 or 60 kilometers. This is getting deeper all the time. I'll show you an example of reflection imaging of the LAB if I get a chance. We can quantify some of the inputs, the thickness of subducting sediment, the incoming plate, how it's deformed at the outer rise, how it may be hydrated. We can look in detail at the properties of the plate boundary, including how wide the cumulative deformation zone might be, changes in pore fluid pressure with depth, and where subducted features are that might be important for controlling behavior. We can understand things about the structure of the overriding plate, including distinguishing different terrains that might be there. And we can also have a kind of a unique view of the composition of the arc crust that can be related to geochemistry. And the list goes on and on. So I'm going to try and show you examples of many of these things once we get a little further down the road. All right, so yeah, what I'm going to try and first do is just kind of go through some really basics of basics about seismic reflection data and wide-angle reflection-refraction data. And I guess the goal of those will be to, if you're not familiar with those, to sort of empower you to look, when you're reading papers about these kinds of data, to understand a little bit more about what they mean and what the limitations are on what's being seen in those data. I'll talk a little bit about how we acquire it, both at sea and on land. And then we'll kind of get in, hopefully spend a lot of the talk really talking about some of the observations that I think are interesting that we're starting to get from these data, particularly on these topics, but maybe some other ones as well. So that is where we're going. All right, so here is a seismic reflection image. It's from Alaska again, and it's across offshore of the Alaska Peninsula. And so I want us to just have a chance to look at this together and understand what's in here. So again, we're looking at sort of two-way travel time and distance from the trench. So here's the seafloor. This is the trench. And hopefully, looking at this image, you can see some other, this bright reflective stuff. A lot of that is sediments above the crust. But hopefully, even in this unadorned seismic image, you can see some other stuff too, particularly this and this. And this is actually, these are reflections off of the plate boundary to depths of, this is about the equivalent of 50 kilometers or something like that. And so when we look at this image, we can kind of think of this as, it's common for us to do all these nice things to visualize the data, like make it all pretty and colored. But basically what this image is 30,000 individual wiggle traces. So it's as if you kind of cruised along on the seafloor with one source and one receiver, and you set off your source, and you recorded some seismic wave that went straight down and came straight back up. And so it went straight down and bounced off of things in the earth and came straight back up. So if we kind of zoom in on one of the 30,000 traces in this image, it would look kind of like this. So you have these sort of positive and negative swings. And the amplitude of these arrivals is related, as we'll see, to the contrast and properties that are in the Earth. But in this image, we're kind of coloring in the negatives are red and the positives are black, just to be able to see things a little bit better. And so our seismic waves go down, they bounce off of things in the Earth, and they come back. And the thing that controls the amount of energy that comes back and the amplitude of those reflections are contrast and properties within the Earth, contrast in velocity and density. And so if we have some P wave that comes down and encounters a contrast in properties, which we're going to express as impedance, the amount of energy that comes back as a P wave or an S wave or is transmitted as a P and an S wave depends on the contrast and properties here and the angle at which it strikes this interface. And so for the most simple case of just a sound wave going straight down, hitting interface, and straight back, we can consider how much of that is reflected or transmitted as all in terms of this contrast and velocity and density of the layer above that interface and the layer below it. But hopefully you can see the bigger the contrast, the bigger the reflected energy that you get back. And so we can think of the Earth, which has different sedimentary layerings, different compositions of crust or other things. It's kind of a series of reflection coefficients. And so where 1 is all the energy comes back and 0 is none of it comes back. And basically, we're introducing some seismic source to that, and you're kind of hanging it on each of these little contrast and properties. And basically, that's each trace of our 30,000 traces in our seismic reflection image. Okay, and so if we now kind of come back to this image again, you'll see in many papers about seismic reflection data, and in this image here, that we're kind of looking down on the Earth in depth, but we're actually looking at two-way travel time, because that's what we measured. So the time it took that seismic wave to go down and come back up. And so, which is of course related to how deep some boundary in the Earth is and the velocity. But if we had done the experiment in this very simple way that I've kind of asked you to understand this image of just going down with one receiver and one source and just firing our source and recording our arrivals and doing that 30,000 times along this line, we would have no idea what this velocity is. There'd be a perfect trade-off of how deep it was to some layer and what the velocities are in the overriding plate. So the way that we actually collect these is not just with one source and one receiver, but with many receivers over a range of distances between our source and our receiver. So here is a seismic ship cruising along, in this case with a source and some streamer. And now you have all these different bounce points of seismic waves off of some layer in the Earth. And so by having many receivers, multi-channel seismic data, for any little given point on the Earth, we've hopefully had a bunch of different reflections off of it at different source-receiver offsets. And as we'll talk about, that's useful for telling us not only so that we can constrain the velocity of the mediums through which these rays are traveling. But it also helps us beat down the noise, because now, instead of just having one source and one receiver, we're recording many reflections off of the same point. And so by kind of stacking them together, we can really enhance our signal and beat down random noise. So that's why we do it this way. All right, so just as an example, if we were to go out, this is off of Costa Rica actually, and set off our sound source and record it, in this case on a 8-kilometer streamer, then this is sort of what we would see. So the very first thing is we're looking in two-way travel time and distance from the source to across this whole streamer, which is as long as 8 kilometers. And so the first thing to arrive is that you just have sound traveling straight through the water and arriving on your streamer. So this is the direct arrival. But with greater time, you start to see reflections off of other key boundaries and also refractions through the very shallowest layers. But it's these reflections which are sort of the main information we're going to use to create images of the Earth. And so I could teach you a whole class about the ways that we try and use these raw data to make seismic reflection images, but I'm just going to give you the one slide version in case. If you want to know more later, I'll tell you all about it. But so to kind of take that shock gather and make it into an image of Earth structure, we first are doing a lot of cleaning of the data. Unfortunately, we record a lot of things besides the signals we want. Swell noise offshore, or storms, or people walking around onshore, and so you have to try and remove all that. So there's a variety of ways to do that, and it takes a lot of time, but it's important to do it right if you want to see deep stuff. There's other amplitude corrections we make. There's a lot of geometry and bookkeeping for where all of our sources are and where our receivers are and where we think all those bounce points were in the Earth. So we can group our data together by all the traces that we think bounced off of one spot in the Earth. And then a large section of what we do here is then really based on velocity, is that we look at the arrivals from different offsets of reflections off of this one point in the Earth. And in the next slide, I'll kind of show you that this is the shape of these reflections, as a function of offset, is based on the velocity of the stuff that it's traveled through. And so a lot of the work that we do along the way of going from that shock gather to an image is giving us velocity information, because we have to explain the shapes of these reflections in order. Then the next steps are that we can, if we know what that shape is and the velocity that explains that shape, we can just flatten it out and stack it together. And so this is the stacking and redundancy that help us also beat down a lot of noise. Another step, which I'm not going to really talk at all about, is migration, and that too is dependent on velocity. So along the way of doing this processing job, we get an image plus some velocity information on the Earth. And so here's your one slide, very simple thing about the velocity sensitivity. So if we have some reflection off of some boundary, so we have some sources and receivers, we move them around to have a variety of offsets between our source and receiver, then the reflection we would record would have this shape. So at 0 offset, it would come in at a time which is just the velocity of what's above it times its height. But then you have this sort of hyperbolic shape with increasing offset as you increase the offsets between these things. And the shape of this is, again, based on the velocity of all the material above that reflection. And so I guess the things I want to emphasize here, well, that this is sensitive to velocity, so we can get velocity information, but also that if the amount, so the main thing that we can kind of measure is this normal move out, we call. So how much the change in travel time you have as a function of offset here. And you can see at really small source receiver offsets, you don't really have a tremendous change in the arrival time of your reflections. But with larger offsets, you can see much bigger changes in time. And so we'll talk about later how awesome and long the streamer of the Langseth is, or of other modern seismic vessels. And the reason that we need those long, one of the big reasons we want those long offsets is that we have much better sensitivity to velocity to much greater depths. And so, and this is why. So hopefully that makes sense. Okay. And so we do this range of steps, and we get images that are like this. So I already showed you this one before. This is off the Alaska Peninsula, but you have both all these reflections. So the black is showing the positive swing on our wiggle trace, and you can see a lot of different structures in here. And then the velocity that's behind this was sort of a byproduct of the processing steps that went into it, and also you have to get it right in order to make things image as well as this. So this is the kind of stuff that we get. You can also do this I've kind of been showing you the simplest 2D case, but you can also do this in 3D. And so instead of having a bunch of bounce points with different source receiver offsets along the line, you're now doing that in 3 dimensions. And then you can image really complex structures along and across the margin. So this is a beautiful and famous example from the Nankai subduction zone. All right, so that was your 5 seconds of reflection data. So this is good. We can make these images of Earth structure, and we get some velocity information. But the depth to which we can constrain velocity is really controlled by the offsets between our sources and our receivers. And so even for the longest streamers that are out there, for the longest streamer we can have right now in academia, something like 15 kilometers. In the industry, maybe you can get to 20-something kilometers. And so the kind of rule of thumb is that gives you sensitivity to velocity to about the same depth. So 8-kilometer streamer, about 8-kilometer depth sensitivity. Well, we want to know much more about velocity structure, much deeper in the Earth than that. And so that's where wide-angle reflection and refraction data comes in. And so now we'll have the 5-second tour of that kind of data. Okay, so here's just very simply the kinds of arrivals you get if we were to go and set off our seismic source, and we again have 2 different layers in the Earth with different velocities. The first thing we would record again is kind of just direct arrivals from our source to a bunch of receivers here. And if we were to plot the travel time that it took those rays to go straight from this source to this receiver as a function of distance, then time versus distance. The slope is telling you about the speed at which these sound waves are traveling, right? The other things that you'll get in this very simple model of the Earth are reflections off of this boundary, as we talked about before. And so those are shown here, here in red. And then you would also get refractions through this next layer, which has a high velocity. And at some key offset, the time it takes for something to go down, refract through this faster layer, and come back, it actually beats the direct arrivals back. And it too has a slope that's related to the medium through which it's traveling. And so for the reflection data that I was just telling you about, we're really focused on this. We're focused on near vertically incident reflections off of some boundary and looking at those in detail. But by having a longer source receiver offsets, longer than we could possibly have with a streamer, we get all of this. And this can tell us a lot more about the velocities of the Earth than we would get otherwise. And so here's an example of a very, very beautiful, this is the typical example, as we say in my field. All of them look just like this, of data recorded on an ocean bottom seismometer. It's barely a subduction zone. It's in the Black Sea, so it was a subduction zone, you know, back in the day. But anyway, so we have but it makes beautiful seismic data. So here we are. We're looking at like all of the arrivals on one ocean bottom seismometer from us cruising across it and firing off an air gun source at a variety of offsets. So we're here from 0 kilometers right over the OBS, which is sitting on the seafloor, to about 70 kilometers of offset. So you can see all of the stuff that I've just told you about. So the first thing you get are just direct arrivals from our air gun array to this ocean bottom seismometer. And with larger offsets, you begin to have refractions through the sedimentary layer, through the crust, which is thin here, and through the upper mantle. And the other thing I should have said is we're again looking at offset versus the time. So the slopes are telling us about velocity, but a common thing people do in the refraction world is that we're very lazy. And so by kind of doing a correction to the travel time, applying reduction velocity, we can make it so that something on here which has an apparent velocity of 8 kilometers per second is flat. And so if you're kind of a crustal upper mantle kind of gal, then you can immediately start to identify things like PN that are turning through deeper layers and kind of quickly recognize stuff. All right, so I kind of just explained to you the first arrivals. But the other stuff you can see back here are a lot of like bright reflections off of the base of the very thick sediment pile and off of the base of the crust. And so this is a rich trove of information we can use to figure out what the velocity structure is. And so if we kind of like combine one of these OBS, these wide-angle records here on the right, so this is kind of the exact same thing we were looking at before, but I've changed the reduction velocity on you to 6 kilometers per second. Here are those travel time arrivals on our OBS. And these are sort of the corresponding-ish ray paths in the Earth. So again, the first things that are showing up are just direct arrivals from the air guns through the water to the OBS, but then gradually have refractions through the sediments, in green, the crust in orange, the mantle in purple, and reflections off of these other boundaries. And so kind of our main one slide worth of steps to go from this to a velocity model of the Earth is we have to do some, again, data cleaning and noise removal in order to see things as beautifully as you see them here. In marine experiments, we actually have to figure out where our instrument is first. You kind of drop it off the side of the ship, as we'll see, and it floats to the seafloor. You really don't, you know where you dropped it. Hopefully you can go back and get it, but you don't know exactly where it landed. But you can use these arrivals to figure out its position on the seafloor. And then a very, very important part of this process is identifying different phases in your data that you want to model. And so in this case, these different reflections and refractions. And so that is pretty much the most important and maybe the most time-consuming part of the whole thing is recognizing, okay, here I see, these turning waves through the sediment, these turning waves through the crust, and to identify other consistent phases on other instruments in your study or other shots. And because those are going to strongly inform the way that you model those data. So that's a very, 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 very important part. And then once you have identified those phases and you have travel times for them, then you can model those travel times to sort of figure out what your Earth structure is. So, okay, so hopefully you recognize this slide back from last week from what looked like an excellent talk from Brandon. I can only see the slides. But he kind of described to you the tomographic problem with this nice simple example of some Earth that we've divided up into these 9 squares, and you have various sources and receivers, and then you can see where you have these ray paths that are traveling through each of these blocks. And by this sort of ray tracing process of looking at, what rays were in what blocks for how long, you can sort of build a relationship between our data, our travel time observations in this case, and the model that we want of the velocity structure of the Earth. And so, here were the ray paths from from Brandon's simple example. Here, the more typical array paths, for example, from a part of the Alaska subduction zone where I had a bunch of ocean bottom seismometers recording waves that had traveled through these different parts of the Earth. And so we can sort of divide up this whole model into a bunch of grid squares and sort of solve for the velocity in each of those grids based on the travel times through those layers. And so what I'd like to do next is kind of, I think that maybe as much as any other kind of velocity modeling effort, that there are very many styles of inversion that people do with refraction data. And so I just want to go through a couple of examples of what has gone into the model and how that impacts what it looks like, and some other choices that are made about smoothing and sort of relative smoothing of different aspects of the model, so you can just sort of get a feeling for how they change what you see. I think that you're all experts in smoothing and tomography from Brandon's tutorial, so I'm sure you'll see how this goes. All right, so the very simplest thing that you can do is called a first arrival tomography. So in the phase identification process, sorry, I'm going to go back a couple slides. All right, the very easiest and most unambiguous thing you can identify on this record are what is the first thing that is arriving. You can identify that without knowing anything about where in the Earth it was or how it's related to these different reflections or anything else. And so a common thing that people do is to actually, before you worry about any of this rich trove of information here that is stored in the kind of things that are coming in not first, is just to do a tomography that's only with these first arriving refractions. And so you're ignoring a lot of information, but then you have almost no ambiguity about what reflections you identified in different parts of the data set and how they're related to one another. And so this is just an example from off of Alaska where we did just that. So we're again looking in depth across the incoming plate. Here's an ocean bottom seismometer. You can see a variety of other stuff in here, but this inversion is just using travel times from these first arriving phases. And so what you get is a very smooth model of Earth structure. So here you have some gradient in velocities below the seafloor that's kind of representing the sediments and upper crust. And then you also, so 6 to 6.5 kilometers per second, these are good crustal velocities. And then you have another kind of the fast change in velocity from something like 6.5 kilometers per second to something like 8 kilometers per second. And so by just using this first arrivals, you get this very smooth model of Earth structure. But you can still see some interesting things in here. But you're ignoring a lot of other information. Now, if we now do the exact same thing, but we're going to include reflections. In particular, we're going to include information from coincident seismic reflection data on boundaries, and also from PMP, this reflection that we can sort of see back here. And then we get this. So now we have, instead of these smooth changes in velocity, we have big jumps in velocity at various boundaries. So we've included explicitly a sediment layer based on the reflection data. So now instead of this kind of smooth gradient from water to crust, you've got a big jump in velocity. And you've got another big jump in velocity here at the base of the crust. And this is because now that we have these reflections we're including, we can have a model that's not just smooth variations in velocity, but has big jumps in velocity. And this is the kind of thing that we get from that. So anyway, you'll see both varieties in the literature. And so by understanding what data went in, you can kind of understand why it might be a very structured model like this or something that's very smooth. But they both have pros and cons. And the important thing that I would want to get from looking at this is that some of the main, although the interfaces are all smoothed over, some of the main features that you see in this first arrival thing are some of the main features I see in this more structured model are also appearing in the first arrival model. Okay, and then yes.
Yeah. So in this, are you just using the fact that there is a reflection, meaning there is a contrast, and then maybe timing information, or is it also looking at the amplitude in some way to get at potentially what the impedance contrast might be?
So yeah, it's a great question. So this is just the travel times, and so the for this case, it's that a lot of the velocity information is coming from these turning waves, from these refractions. But even the time and shape of these reflections also gives you some information. But for this scale, you probably can't see it, but for some of the details of the interface geometry, we get that from the reflection data. But we did make a very important choice, and that's that, I don't think I have a slide about this, but another, if you do choose to include secondary arrivals in your inversion, you can choose to either make them represent velocity steps, which we have done here, so that you're explicitly saying, okay, now the velocity is allowed to sharply be a discontinuity, I guess, across this boundary, or you can have them floating within smoothly varying velocities. So you can make other choices that would control this. But you're right, if I wanted to get even more information on really how sharp this boundary was, by looking at the amplitudes of these reflections, you can get much more information. So.
Kind of a related question, I guess. So teach us, as people who don't do this, how to be skeptical about these models in a reasonable and intelligent way. Because you just talked about, there has to be a choice made about where the interface goes and the way that these various pieces get fed into what is the final result. So can you just kind of walk us through, as if you were to see an image like this from one of your colleagues, I mean, how, what should we look for and sort of be, in order to be kind of a skeptic?
Okay, great. I'm glad you asked that. So I'll answer that in a couple different ways. So, once we have a model like this, if we wanted to evaluate how confident we were of our resolution, for example, we do very similar things to what's done in the passive seismology world, and that's that we'll do checkerboard tests, or if you have particular features you see, you'll do a synthetic test with your data to reproduce that feature. And so I guess if I were you and looking at these things. In this image, I don't have it on here, you have ocean bottom seismometers that are spaced at about 10 or 15 kilometers per part. So if I don't have a checkerboard test in here, but if I were to show you one, if there are little features in there that are below basically that spacing, you don't want to really make any sense of that. Another very a big source of uncertainty in this model, for example, is actually the lower crust. So if I go back many figures to this figure, we can kind of look at really in detail where our ray coverage is within our model. And so hopefully what you can see in this is the same model, is you've got like a lot of turning waves here in the upper part of the crust, and this isn't exactly the right one, but it would look this way. And in that kind of final model, so you have turning waves that are in the upper part of the crust, and you have reflections off of the base of it, and then refractions through the underlying crust. And so you can have a trade-off in velocity within the lower crust of how thick you make it and what its velocity is. The reflections off of the base of it and the refractions through the underlying model tell you some stuff, but it's just not as well constrained as other parts of the model. So for example, in this model, we actually, I'm like, man, I'm going to share all the dirt now. But an interesting part of this model that we don't understand yet is this kind of reduction in velocity in the lower crust. And you can see the feature in the data that brings this out is that there's actually a little bit of a shadow zone here between these refractions through the upper part of this layer and when the MOHO comes in and PN emerges. And so that could be, so the magnitude of that low velocity zone and its shape are something that is uncertain in this. And so if someone wanted to run around and say a lot of really detailed things about this velocity, that's something that you shouldn't believe. And then another test that is really common in our field now is to look at uncertainty is that you take many different starting models and you run a bunch of different inversions and you add some perturbations to your travel times. And it's like a Monte Carlo approach that's common in many other areas. And then you can take the average of all the different results and look at the standard deviation of all those results. And that too can tell you which features of the model are the most robust and which aren't. But I think that, yes, I'm answering your question in a very long way, but I guess what I would say is like for one, to look at where the ray coverage is and what kind of ray coverage it is to understand what parts are constrained, to sort of think about the experiment geometry in terms of the scalings of structures that you could have, and then to kind of carefully assess some of those other tests. And I guess this dovetails a little bit into my next couple slides here that I wanted to show. And this is sort of the perfect example for, is that we also make a lot of other choices along the way in terms of our modeling approach. And so especially when you have a model that has layers and velocities within those layers, you can make choices about the, how rough you want your boundaries to be versus how rough you want your velocities to be, how much horizontal smoothing versus how much vertical smoothing. And so you really have to sort of read that methods part of the paper to see what preferences someone kind of probably imposes on their model with those choices. And so to kind of illustrate that, I just had a couple slides from an old data set collected along the Aleutian Island arc in the 1990s. And it's a really cool and unique data set, but this is the sparsest of the sparse of data sets. So these red triangles are showing all of the instruments, which were, mostly were just on islands. And so in some cases, you've got like 100 kilometers between these instruments. So in a case where you have a really dense experiment, maybe your choices about those sort of smoothing or other things matter less. But when you have a really sparse experiment, it matters more. And so this is showing the exact same data, and this is a kind of a simple one, just looking at like how well we actually are fitting the data. So the common way that we express that in the refraction world is with chi-squared. So we're just looking at what the difference is in our predicted and observed travel time scaled by our uncertainty in those picks. And so so in principle, you want to fit that thing to 1. You want to explain the data within its uncertainties. And so here's a model along the Aleutian arc crust of that. But if we relax that criteria, in this case we say, oh, we have this crazy 3D geometry of the sources and receivers and blah, 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 then you can see that you have the same features there. They're just much less rough. But maybe a more instructive case is that a common choice that we make in terms of smoothing and active source data sets is you have some trade-offs. So this model has 3 layers in the crust here, and we've allowed there to be velocity discontinuities at those layers. So to satisfy our data, like in the most extreme cases, you could say, I would rather have really, really rough boundaries between those layers and really smooth velocities within the layers. Or I think that the layers are really smooth and the velocities are really rough. And so these are those 2 kind of end members. And you can see that you get, well, when you decide that you think there should be rougher boundaries and smoother velocities, then lo and behold, that's what you get, is a little bit rougher and a little bit smoother. But I think that another important thing, and this paper by Harm is really nice, because what he did was he showed a bunch of different choices that we made in that paper about these kinds of smoothing decisions and what the impact on the model was. But if someone does that, then you can look at the features that persist regardless of all those choices and say, okay, this is a robust feature. So in this paper, we were really excited about these very high velocities and the lower crust. And no matter what decision we made, we got some high velocities and lower crust.
So on the last slide, there was uncertainty. And how do you determine uncertainty for a travel time that someone pointed to with their hand?
You can do it in a couple different ways. So one way, and actually might be the most common way, is to do it visually. Because one of the most common sources of uncertainty in making a travel time pick on these data is, let's see if I can find a good example. You can broadly see, oh, this is my refraction, but is cycle skipping. And so in some cases, you can sort of look along the refraction and sort of just gauge, like, oh, if I were to pick this in a different place, like what would that uncertainty be? People also look at variations in amplitude as a more automated way to kind of determine what the uncertainty is, but that actually tends to give you smaller uncertainties than a visual assessment, if that makes sense.
Quick question. I didn't really catch why there's symmetry on the mound on the far right, so that's presumably an artifact of the data collection, or?
For symmetry here?
Yeah, about this water valve.
Yes.
Yeah, it's a mirror image of itself.
That's right. And so in this case, this is very symmetric because the geology on both sides of this thing were the same. So we started over here 10 kilometers to the left of where this OBS was and drove across it. And so the geology didn't change very much on either side, and so then the travel time branches were also pretty similar.
So I have a question about the absolute value of those velocity, because for teleseismic tomography, because we're dealing with undetermined problems, so we usually use damping, and then those absolute velocities are probably not as reliable as the counters. So people tend to describe blue versus red instead of absolute value. But for active source, I guess you have way more data. So I just wonder how reliable those absolute velocities.
Very. We also have damping and smoothing, and so I think that the variations that we see could be considered kind of a smoothed version of reality. So we may not capture the very highest and very lowest velocities in some cases. So, but that's another thing that you can gauge from something like a Monte Carlo test that I described, is to see what variation in velocity you could have in one layer, and it would still describe the data. So, okay. So now you know some of our dirty secrets.
Sorry, Donna, can I just ask a question about
Yes.
that previous slide? So what should I interpret from this in terms of what structures are there, and maybe laterally? It seems like I would believe that they're layers, but laterally, what should I interpret from this?
So I think that the broad pattern of velocity, of changes in velocity here that you see within those layers, that you can see in both of these results that had very different choices, are what to believe. And so the fact that you have something that's relatively high velocity here and you had a big kind of lateral change in velocity is something that I would believe. But some of that kind of scale of things. Obviously, the details of some of these, in this sort of extreme sparse data set case, some of the details of like topography on these layers or really smaller scale variations in velocity, those are things that you wouldn't want to put a lot of stock in. So. Oh, okay.
Sorry, can you go back to that slide? So I'm assuming in terms of inversion, it depends on the size of your box that you choose as well. So that's why I'm guessing those white boxes are where there's no ray coverage or whatever, or?
The boxes are in fact are smaller than that. We've kind of blocked out the low ray coverage ways in a less blocky way. I think in this inversion, we had variations in the grid size with depth from something that was like a kilometer or so near the surface to a couple kilometers at depth. So, but yeah, that's an important also choice you need to make about when you
the grid spacing.
Yeah.
Right. I see.
Okay. So now I'm going to race. I want to make sure I get to the results. So I'm just going to race through some things about how we collect the data, and hopefully you'll keep in mind the things that we want, the attributes we need from our data to have it tell us what we want to from the last section and this section. But we can do this on land and at sea. In the ocean, we almost exclusively use air guns to make our sound waves. So I'll show you some things about that. On land, we can use a couple of other options, of which explosives are totally the most fun. And then we can record these sound waves on a variety of things. So in the ocean, it's streamers filled with hydrophones or ocean bottom seismometers. Onshore, it can be a whole spectrum of geophones or nodes or other more traditional seismometers. So for the air guns, so we'll start with the sources. So in the sea, we use air guns. And so in this way, we deliver compressed air to this air gun. Sounds so violent. And and basically you fire the air gun and it sort of blows this bubble that collapses. And that's what makes your sound source. And depending on how large your gun is, you get kind of different ringiness. And so by having many different guns of different sizes, you can kind of make a source that's as close to what we really want in the Earth, which is kind of a spike, and put that into the Earth. And so you can really tune these both for their frequency content, for how strong they are, and how clean they are. And there's trade-offs between a lot of those things, depending on if you want to see something shallow or something that's deep. And so this is the air gun array of the Langseth, our main seismic marine seismic facility in the US. And basically you have, in this case, there's 36 different guns of varying sizes. This is a weird picture, but this is on the ship looking at a black float, and then there's chains below it, and on it is hanging all of these different air guns. And so their depths and relative timing and everything else have been like carefully designed by the late great John Diebold to make as sharp of a pulse as you can. And so here's just looking back behind the ship. Sorry, this photo is fuzzy, but you can see these sort of black snake things, and these are the floats, and all the air guns are hanging down below them. And on land, we have a variety of options. So one is a vibra-sized truck. This is like this mega truck that lowers a plate onto the ground, and then it sweeps through a bunch of frequencies from something like 6 or 8 hertz up to whatever, 80 hertz. You can control that frequency band, but you know that frequency sweep perfectly, and so you can remove it from your, account for it in your processing. And then finally, you can use explosives. So this is, I had the opportunity to do this about a year and a half ago or 2 years ago in a project I led. So you drill deep holes and you load them with the explosives. So here's Galen Cape from the Seismics First facility at UTEP. And all these canisters contain kind of an ammonium nitrate emulsion, and then there's some sticks of dynamite in there, and you load it all into this 100-foot deep hole, put a bunch of dirt on top of it, and you set it off in the middle of the night, and it's awesome. So I had, unfortunately, since it's nighttime, the videos kind of suck because you can't see anything, but what you can hear is like the beeping of the box that actually sends the, sets off the blast, and then kind of a low frequency like thump, and then a bunch of people going like, ee, wee, that was so awesome. So instead of playing that for you, I have just replicated it. But anyway, it makes some really beautiful data. And so at sea, we can record sound waves for reflection imaging on streamers. And as hopefully you now totally can see from the earlier part of this talk, the longer the streamer, the better if we want to get both velocity control and depth. And so we store those streamers on these gigantic reels, which we unspool into the ocean. And it takes days to actually put out something like 8 kilometers of cable behind the ship. And then you have 15 kilometers of streamer, and so like figuring out where it is and controlling its depth is actually somewhat of a challenge, because you have a tail buoy in the end, you know where that is, and you hopefully know where the ship is, but everything else is underwater so that you're away from the noise. And so we have all these other stuff that we stick on there. These are called birds, and they have little wings that can control the depth. And you can put acoustic sensors on here to look at relative positions between different streamers, and also compasses to see what direction some part of the streamer is. And then you can sort of solve for where it is in the oceans. And we also use ocean bottom seismometers. I think that Doug and others have, I'm sure, introduced these. They're still magic to me. You just have a package here that has a seismometer and logger and hydrophone and other goodies in it, and you just dump it over the side, and miraculously you come back and you can pick it up, and it did something good. And then we can also use a variety of seismometers onshore. I think that Doug and Brandon introduced you to both kind of more typical seismic deployments, but also things like nodes, which are these higher frequency and smaller and quicker and easier to deploy seismic stations. So I'll just cruise past all that. Okay, so now how much time do I have? Like 20 minutes?
Yeah, I mean, we'll go to 12, we go to 12:30.
Okay.
Yeah.
20 minutes. Okay. So now that was how we do it. But now I just kind of wanted to run through and just highlight for you some examples of results that we get from these kind of data in different places. And so what we're going to do is we're going to first start with inputs to the subduction zone, look at some variations in plate boundary properties with depth, and then look at arc structure. So those are the main things I hope I'm going to quickly manage to go through and talk about to you. All right, so we've seen this image many times already. This is from off of Central America. We can already see from the bathymetry data that the incoming oceanic plate is faults as it bends and subducts, and we can see that really beautifully in Sammer's EM results that that he and Carrie have shown here. But you can also see that in the seismic reflection data across here. So here's the seafloor, and you have all these sedimentary layers which are offset by faults. And very interestingly, in this image, you could also see these reflectors that Ranero and colleagues interpreted to be the continuation of those faults through the crust into the upper mantle. And so and then the other, even more convincing to me, observation that those faults continue from the seafloor through the crust into the upper mantle is the change in upper mantle velocity we get. So this is from Ivan Dick and colleagues. We're looking at that same section off of Central America. And what you can see is that both if we look at the velocities in the upper mantle, which are here, we go from 8 kilometers per second and have a reduction of almost a half a kilometer per second once we come into the middle of this most faulted and bent area. And as Doug described to you before, one way that you can change velocities in the upper mantle is to add water and form the mineral serpentine. And so from relationships like this, you can, if you assume all of that change in velocity is from serpentinization, you can make estimates of how much serpentinite and how much water is in that plate. So here's just the change in velocity that these guys saw with respect to kind of a reference velocity structure as they approach the trench. So you see this big reduction in upper mantle velocities. You also see changes in crustal velocities too, which get a little bit less attention, but I know are of great interest to some people here, including me. But I think that now, after that set of work, there's been a lot of focus in our community of really seeing, understanding this faulting and hydration story. And so I think Doug showed you this too. This is work from Harm van Avondonk, but they collected a refraction data along the trench. And one of the really cool things that they saw in their model, which is shown here, are changes in velocity within the upper mantle along the subduction zone. So they have more slower velocities here to the north and to the south. You can actually sort of see that mirrored in the amount of bending faulting as well. And they related that to changes in serpentinization and in water that was being delivered into the subduction zone, and saw some correlations with the chemistry of volcanoes on shore. So that's really cool. One of the things that I think this has been shown too, but from our work off of my favorite subduction zone in Alaska, we also see big changes along strike in the degree of faulting and hydration of the incoming oceanic plate. So here I'm showing you two velocity models from these two different areas, where in one case we have lots of bending faulting in the reflection data and a nice big reduction in velocity in the upper mantle, whereas on the other transect we have much less faulting and kind of a more complicated velocity structure, but not a marked decrease like we see in the Schumagins. And in this case, especially for these changes in mantle hydration, we see a big difference along the margin in the amount of intermediate depth earthquakes, which in one way to interpret that is that for a kind of thermally identical plate, that just over in this area where we have more of water, we think in the plate, that there's more water available to dehydrate and drive things like dehydration and brittlement here than here. So we also see correlations with behavior too.
Can I ask you a question about the last slide? How robust are your crustal seismic velocities? Because what I find intriguing is that where you have less mantle velocity reduction, you also have less, or you have also less crustal.
Yes, that's right.
Reduction.
That's right.
So I'm thinking of Carrie's talk about characterizing the hydration of Nicaragua, where there's a strong suggestion that the gabbros also get wetter.
So the part of kind of referring back to what I told you before, the part of the crustal velocities that I would say I feel most confident about are the kind of the upper part of this. And indeed, this is a meaningful difference. You have a reduction here in the upper crust compared with out here, and that seems to be less of a pattern here. So I would say that is a robust feature. And yeah, here this is associated with a little more uncertainty in our models, so I guess I would be a little shy to make too much of the lowest crustal velocities, but it's true that those two show a reduction, if I'm looking at the right thing. All right, and then a final example from the hydration side from a really warm member. So Alaska is on the kind of middling side of things with a 50-million-year-old subducting oceanic lithosphere. But of course, Cascadia is very hot and young. And these are some results from Shosho Han with the reflection imaging and from Greg Horning from refraction data here off of Oregon. And the pretty interesting and different thing that they see here is in this much hotter subduction zone, they see really very little evidence of hydration of the upper mantle. The velocities stay pretty high except in a few different spots, and these are kind of located along propagator wakes or other structures in the plate. And so the big change that they infer are changes. They think that if there's hydration, it's all in the crust. And they see evidence from their models of a change in crustal velocity. And I think that they really are thinking even the upper crust. They also image some very nice faults within the crust, kind of within this bending area too. And just as a, before I leave behind the hydration story, another kind of puzzle for us in our community right now is that the way that these bending faults appear in our data can be really different from place to place. So here in Cascadia, and in the example from the famous Renero example from Costa Rica, you can actually see some nice reflections off of some faults that are in the crust. In many other places, with the exact same quality of data and types of processing, we don't see any reflections off of these features. And so there's some feeling that these could be real changes in fault properties, but we really don't yet understand. I don't know if we have enough data to really systematically think about how they could be different, but it's a little bit of a conundrum that the aficionados have been kicking around. All right, so now I'm just going to quickly march you down the plate interface. Another thing we feel like we can do well from these data is look at changes and properties of the plate boundary itself, down dip and along strike. And we'll sort of start on the shallow side and then move down. And so again, I will take you to Alaska. So one of the, so I've shown you this image now many times, and one of the kind of striking features that we saw in this image is, for one, you can kind of see this incoming sediment section. It's nice and continuous. This is the place where you have very little bending faulting. And that sediment section is coming down, and the upper part appears to accrete, and then the lower part kind of appears to continue down. And you can see, hopefully, do I have a zoom in? I always like to zoom in. Like people show like these fuzzy, low-resolution images of seismic reflection data, and they're like, look at that. And you're like, what is that? But here, so now we're zooming in again. But hopefully you can see this, and in different places this. And these are, we interpret reflections off the top and base of a subducting sediment layer. And it has relatively low velocities. Normally in a pile of sediment, velocity should increase with depth, and it doesn't. And so we've inferred that the best way we could come to explain these low velocities, similar to studies in many other subduction zones, is that you have variations that you have elevated pore fluid pressures. And basically you have more porosity there than you'd expect for normally compacting sediments. And so by using the incoming sedimentary section far away from the trench is sort of a way to come up with we can assume that there's no overpressures there and come up with a relationship between velocity and pore fluid pressure there, and then use that relationship in the trench to see how pore fluid pressure varies. And so what I'm showing you here are observations of velocity within that subducting sediment channel. And each of these colored lines is showing predictions for different possible pore fluid pressures expressed as this lambda star, which is sort of a ratio of pore fluid pressure and other things. So a lambda star of 0 is no elevated pore, is hydrostatic, and the lambda star of 1 is like lithostatic. You can see that for our data, it's kind of best explained by some relatively high velocities. And in our case, we only have lines, 2D lines, and so we can sort of compare lines along the margin and see big differences in these plate boundary properties and the shallow part along strike between where you have a thicker and unfaulted sediment section coming to the trench and where you have a thinner section, which has a lot of bending faulting coming to the trench. And so here, you have this nice low velocity zone. Based on our streamer length, we don't know, we can't be sure about this, but we can down to 8 or 9 kilometers. This is where we have sensitivity. But you have a very different story further to the west, where you have this irregular and faulted up section and a very different looking plate boundary without evidence for pore fluid pressure. So we kind of see an impact on what comes in and what it looks like. If you have 3D data, this is from some really nice new results from Nathan Banks and his colleagues from a 3D data set they collected off of Costa Rica. they also see changes along strike and down dip, they think, in the shallow plate boundary properties. And here we're looking at kind of a slice along what they interpret as their plate boundary through this three-dimensional seismic reflection volume. And what they're plotting here is the reflection amplitude. And based on what we've talked about here and in other talks, the amplitude of those reflections is going to be based on the contrast and properties there. And so they relate these, very, high amplitudes, or I should say very low, so very negative high amplitude, but low, reverse polarity, high amplitude reflections to variations also in fluids and pore fluid pressure along this boundary. And so in the very few places that we have these kinds of special 3D data, you can look in even more detail at the patterns and how they relate.
How do you get 3D data?
It takes forever. So in the ocean...
What is it that you're doing different from what you showed us already?
So instead of, when we go out and collect 2D data, you have usually one streamer and your source. And you just go along a line and then you're done. For 3D data, instead of, we kind of want for every kind of little spot in the Earth over some volume to have a range of reflections in there from kind of different azimuths and at different source receiver offsets. And so the slowest way to collect it is with one streamer, and you just go around and around in one little box for 6 weeks. That was my second cruise. It's like Groundhog Day. You're going over the same real estate over and over again. But a more efficient way is that you actually tow multiple streamers. So the Langseth is capable of towing 4 streamers at 100 or up to 200 meters apart. And then every time you fire your air guns, you're kind of blanketing a little area underneath the ship and with bounce points from different places you want to cover. But it still takes a very long time to cover. This is not like a gigantic area here. I think this is 40 by 15 kilometers. And it took, I think this took them 6 weeks to cover it. Because you can't do it halfway. If you want to have a nice imaging like this, you really need good coverage of every little position in that box. And so after you kind of just go all around it in a regular way, you look for where the gaps are. And then you start driving around like crazy people over the gaps to fill those in. And then you're really, really ready to get off the ship. But the data are awesome. But then they have a more complex processing sequence to kind of deal with the three-dimensionality too.
Yeah, how can you be sure that the reduced reflection amplitude with depth is not just a reduction in resolution due to the greater depth of the interface and maybe some high attenuation of the waves?
I think that's a very good question. And I think that here what I think that these guys would say if they were here is that if you just have a gradual reduction in amplitude over depth, I think then you have to say, oh, it's deeper, the imaging is harder, maybe it's not as good. But and a couple, I think both here and in Nankai, they see that change over really short depth distance. And some of the other variations in amplitude they see kind of make geologic sense for where you'd expect there to be bigger contrast in properties. So I think part of it is looking at the kind of types of patterns and how they make sense geologically. But yeah, I mean, for some aspects of this you can correct for, like a common correction we do is for like spherical divergence and things like that. So that hopefully the amplitudes are really telling you about real changes. But yeah, it's true that other things can go into this reflection amplitude besides plate boundary properties.
So almost always with these 3D experiments, I've seen the reflection boxes, the imaging boxes in terms of discontinuities. Do they get velocity information from when they do the processing on these? And is there, I mean, I guess, does it give you a depth range that's useful for interpretation? Yeah, so in the, you can get very nice and do a much better job with velocities from these kinds of 3D data. Like the Rolls-Royce would be a 3D pre-stacked depth migration of this, where you would get both, which enables the imaging of the most complex structures, like in a subduction zone, but also it give you kind of a 3D velocity volume that could be very, very useful as long as at the depths where you still have sensitivity to velocity. So it still may not help you with, much, at a lot of the most deep structure
I think this was like a 6-kilometer streamers, I think, but yeah, but it does. And in some cases you can actually get, and the industry, they'll actually get also constraints on anisotropy a little bit too, because of the spread of azimuths in your bends. And if you have a long enough offset, you can see things like transverse anisotropy. So, okay. 5 minutes. Okay. I have to get to the arcs, otherwise I'm going to feel really bad. So, but I will very quickly say that another very interesting thing we see at larger depths in many places, and really first recognized by Milad-Nedimovich, are changes in the reflectivity of the plate boundary. And so this is an example off of Cascadia, where from all of these different lines shown here, they found that in one part of the plate boundary had this really simple and bright reflection and very narrow. So this is kind of telling you that there's a really pretty simple and thin structure that's actually there that made this reflection. Whereas at larger depths, you get this kind of bigger band of reflectivity over 1 or 2 seconds. And so, and where in this case, they interpreted this change in reflection character to possibly a change from brittle to ductile deformation, where this kind of big, thicker band of reflectivity is kind of representative of a big ductile shear zone. You can definitely see there must be some change between these places. And kind of lo and behold, as people look at a lot of other subduction zones around the world, we see often a very similar pattern, sometimes at different depth ranges and of different styles. But here off of Alaska, we saw something very similar. So I'll zoom in, but on kind of this shallower part of the plate boundary, this is around like 15 or 20 kilometers, we also see big, honkin', beautiful, bright reflection. It's 20 kilometers down. And when we model that thing, it's best explained as a really simple low velocity zone, like 100 or something meters thick. At greater depths, you get this much more complex, so this is now the plate boundary, and you get this much more complex band of reflections that are modeled as sort of a 3 to 5 kilometer thick set of kind of complicated layers. Here, these changes happen at depths where it's too cold for us to expect that we have really a ductile shear zone. And so from comparing with seismic behavior as we know it, and with and other constraints we have on how the plate boundary is behaving, we sort of imagine that as sort of a broadening of deformation, which looks like it happens where the plate intersects the four-arc mantle wedge. And sort of associated with these changes in properties, we see changes in seismicity, where this like really simple bright reflection is like in the middle of the last great earthquake rupture zone. It's in the middle of the lock zone that Jeff Reimuller showed us earlier this week. And it's relatively silent. It doesn't have a lot of seismicity. Once you go to greater depths, you start to have more small thrust earthquakes and eventually slow slip events. And so it really looks like you have a change in properties of, or change in behavior that relates to these changes in properties. Yeah, sorry. Sure.
Okay. I just wonder, you make the case that the later interface is kind of more fuzzy and broader, but it seems it's deeper and also it's deepening. So is that, I guess, seismic reflection is more sensitive to near horizontal interface, right? So is that a resolution issue or something?
In this case, it's not. But you're right that because if you have changes in depth, then it does get more complicated. Here, I think we're still within a realm of dips where we are well constrained for our. It's again sort of based on your source receiver offset, how well you can recover dipping features. But and if I showed you other parts of our data set, we sort of see that transition in places that have the same dip in other areas of the study, and so that gives us some confidence that it's not just the dip. And so we have been very inspired in trying to understand what this looks like by exposed megathrusts on shore. And in particular, things like this excellent figure from Sarah's talk of showing how maybe, or this is going to be my interpretation of it, so she can tell me if it's wrong. But you have maybe some more localized deformation zones at shallower depth, but then this kind of broader and more complex melange with interlayered materials at depth. And so we think that these are the kind of structures that might be producing the sort of seismic reflection imaging characteristics that we see. And so another kind of interesting question then for us is, with the frequencies that we have, we're imaging a structure that's like 100 to 200 meters thick in our reflection data. And if you look at kind of the same general real estate and receiver function images, so these are not from the exact same place, so this is not a totally fair comparison, but they often see kind of a 2 to 4 kilometer thick low velocity zone. And so I think another challenge for us is sort of reconciling how these different frequency data sets are seeing different aspects of the plate boundary and its properties. So I think that's another challenge I see. Okay, and so finally, I'm gonna go to the arc. And so another thing that we would all wish to know, I wish to know, is what's the kind of the bulk, what are the controls on the bulk composition of island arc crust, and how do the compositions that are what is in the middle and lower crust, and how does that relate to the compositions of things that are coming out of the top? And so maybe the best studied island arc that we have in terms of refraction imaging is the Izubonin arc. And so what I'm showing you here are velocity models across that arc. So you can see the subducting plate, and this is the main volcanic lineament here. And again, it's contoured by velocity, so this is all the kind of crustal section, and then this is the upper mantle. But the amazing thing they have, and this is the only place in the world we have this, is this along strike profile. And here, you have instruments that were spaced at like 5 kilometers. This is stunning. And the amazing thing that they saw in this image were these big variations in crustal thickness, and variations also in the velocities within the crust. And because of the amazing density of data they have here, these are things that are really pretty well resolved. And I believe, as Doug and Jeff talked to you about before, in these kinds of settings, we want to use crustal P-wave velocities to understand something about composition. And so broadly, variations in P-wave velocity correlate, for example, to changes in silica content of a rock. So the more silica you have, the lower your seismic velocity. And then with more and more mafic compositions, you get really higher velocities. That's good. In detail, especially for these more mafic compositions, you can see that a lot of different rocks over, in this case, a wide range of silica contents have similar P-wave velocity. So there's some uncertainty, but this is still a useful tool, and I'll come back to the uncertainty part. But otherwise, we have this line I showed you before where we had like 100 kilometers between our instruments. So the resolution of this versus this is a whole different world. But even from these more sparse data sets we have in other island arcs besides IBM, we see pretty big differences in the overall velocity of the crust. The elutions are much faster than this crust. We see changes in thickness, both of course along this arc, but between elutions and IBM, elutions are a little bit thicker. And so I think that this image is a real call to action for us to see if there's similar things going on in other island arcs. And so the cool thing that they were able to do, and we were able to try to do in the elutions, is see how those variations in thickness and velocity structure of the crust relate to changes in the composition of magmas coming out the top. And so what they're showing here is kind of the average weight percent silica for volcanic rocks, along this part of this section of the arc. And then here they're showing average P-wave velocity just in the let's see, in the middle crust is the dotted line, the entire crust is the black line, and changes in the thickness of the middle crust. And they see this pretty interesting a correlation between the most basaltic volcanoes and the lowest velocities in the crust. And we, in our much lower resolution and dicier attempt, also think we see something like that. So I showed you before these very high velocities in the lower crust, and those, bearing in mind our crappy resolution, there's a hint of a correlation with more siliceous material. So, a geophysicist interpretation of this is that if you have constant composition of the magma that's coming in, to make something more felsic at the surface, you have to leave more mafic stuff behind. But if we had more data like the IBM, we could make more meaningful comparisons between crustal velocity and compositional variations and what's coming out at the surface. And so P wave velocity is non-unique, as I tried to show you. And so I think that going forward, the things that we can do better are to combine that with constraints on S wave velocity and VPVS. That's a little harder in active source land. We haven't talked about that, but especially for marine experiments, we have to get conversions between P and S wave energy to get S waves. But through new passive source imaging techniques like ambient noise tomography, they can look at S wave velocity variations at similar scales to our P wave velocity variations, and we can get a much better idea on velocity from that. And I think that looking both at, in more detail, at patterns of velocity with depth and along strike, and comparing those with expectations for sort of simple magma evolution models, that might take us further too. And so this is, yeah, you'll all have to forgive me. This is my attempt with P-melts to kind of consider that. In this case, to consider the role of water in controlling the changes in velocity that we saw. And one of the big things we saw was that high velocity blob, and we think it had a big step in velocity at the top. And so that maybe one way to produce a really sharp increase in velocity with depth would be that if you add water and you suppress plagioclase crystallization, you get a big thick pile of clinoperoxenite and then a sharper plagin that might make that change. So this is obviously not the only scenario that would produce those velocities, but kind of doing these exercises, maybe we can get a little bit further down the road. And so I think to leave time for questions, I'm going to say, oh, remember how cool that was from Brandon's talk? And now sometimes this is like a new realm that, with a better and denser data quality and bigger sources, and by looking, that people are also even starting to see reflections off of things like the LAB in a couple settings. So I think we have a lot of opportunities moving forward to, I think that with denser data sets that we can see in many settings, and in 3D, could see things in much more detail, and it also opens up the way to do really amazing things. Like this is work from Adrian Arnolf at UTIG, who's done waveform tomography with streamer data off of New Zealand, and you can see just these really fine-scale changes in velocity structure. I think Doug showed you an example in his talk too. And obviously by integrating more of these things, as we increasingly have co-located data sets, we can actually get a little bit farther. So thank you.
Postdoc and student questions first.
I guess you were getting at this to some extent at the end when you were talking about the velocity structure of the crust, but magma bodies, is this something that people are working on at arc volcanoes, and can you see them in these data?
I should turn that over to the biggest magma body enthusiast I know sitting in the front row, Brandon. But actually, there's not very many places where, like the challenge in island arcs in principle, yes, you could image magma bodies with this method. And so, for example, at mid-ocean ridges, a lot of people are doing really excellent work to quantify their depth, the amount of melt, and their geometry, and all of that. In arcs, it's hard because the volcanoes go over land, or they're above water. So you have it's a more challenging acquisition problem. So you could try and do, go out to Akatan and try and imagine doing an active survey across those arc volcanoes. That'd be really challenging. And then, another thing people do as well is try and, if you do have a volcano and it's surrounded by water, is to sort of undershoot them. And so you can see some things, but then if you can't get right on top of it, the shallower magma bodies and the constraints you have on them wouldn't be very good, but it would be a cool thing to do.
I wonder what your take about the lateral change in serpentinization. What kind of the mechanism that create that? And you showed that cool correlation with the earthquake, the deep earthquake. So you basically assume that the same mechanism acted when that slab was around the thread, if I understand right.
Yes, that's right. So in this example, where sorry, I don't have the reflection data here, but if I did, what you would see is that there's much more bending faulting here than here, and and because you have a difference in the amount of faulting, if those faults are really pathways for fluid into the crust and upper mantle, then you'd expect differences in serpentinization, and that's, we think, matches what we see from the velocity models. In this case, the overall age of this plate is kind of the same. Many things are the same along here, but one of the things that is different is that you have maybe a different orientation of pre-existing structures with respect to the trench, where in the west you have, if we take these magnetic lineations as sort of a proxy for the orientations of faults we would have expected in the oceanic crust, that you'd have more favorably oriented pre-existing structures here to reactivate, which might lead to more pervasive faulting in comparison with this area where things are aligned more, more obliquely to the trench. So that was our interpretation. But it's certainly the case that as you look around the world that there's other kinds of complexities that can control where you have hydration. So in Cascadia, they think these propagator wakes might have been very important as a localizing where you have hydration of the plate. People invoke seamounts. And so I think that our biggest takeaway from this is just that, and I think from this and the other examples I showed, is that there just is quite a lot of heterogeneity in hydration. And so that's something that then gives us a challenge and opportunity to think about what the consequences for that are in the Earth. But I mean, the thing that we would really like to know, so we can see from these images changes in, we think, if you assume that whole velocity reduction is from serpentinization, changes in the total amount of fluid. But it'd be great to know, is it localized along joints, or is it more distributed? And so I think there's a lot of other, next questions. So. Are you a student?
I thought we were done.
Okay, I'm sorry, I'm teasing.
Okay, is there another student or postdoc who has a burning question?
Wow, I dodged that one successfully. This will probably be much harder.
Yeah, thanks, Torsten. Yeah, just a quick question. So I think the imaging you're doing of the interface, the subduction interface, is super exciting, really, really cool. So like in the, with the availability of the data and stuff you have now, like what's the best case scenario? Like what's the finest resolution of structures that you can image in from data from stuff like that?
That's great. So actually, let me go back to this image. So we put a range of frequencies into the Earth, but higher frequencies are preferentially attenuated with depth, so that to get reflections off of features at 20 or whatever kilometers depth, that tends, at least in our data, we're kind of in the 8 to 15 hertz kind of realm, and so then that gives us we're still a resolution that's more like tens and tens of meters sort of resolution. At shallower depths, where you can still have higher frequencies that haven't been attenuated, you can look in much, much more detail at the properties. But at least for, I think that's kind of our best case scenario now of what I would say we could do usually. It'll vary from place to place, but thanks.
Torsten?
I was just wondering as to the inversions and your example of the trade-off between the structure and velocities, of how much of these inversions are based on a Bayesian approach, like I guess industry is doing regularly, where you really have, some sort of nonlinear inversion that moves the interfaces around, and then you solve the forward problem over and over again to sort of get a better feeling for how much, the trade-off between the impedance contrast and the velocities, and how much the data actually wants these reflectors, rather than having to make these a priori choices. And if you could comment a little bit how easy it is to sort of move the next step with these inversions.
Oh, there's a couple things in there. I don't think that those kind of Bayesian inversions are very common in the active source community now. I think that we to kind of consider things like the impedance contrasts and amplitudes. The way, all of what I've shown you from my work is all travel time tomography. But clearly the next step is full waveform inversion, where you can actually have all the constraints of the amplitudes there. And for that, we need denser data sets than we commonly collect. So with seismic streamers, you can do that. But you need a really, really, really good starting model from travel time tomography. And so a limitation has been that to make that starting model, which people use travel time tomography of the streamer, you're then again still limited in how deep you can actually constrain the detailed structure from travel time tomography before you can do the waveform inversion. So with really dense OBS deployments, then you could actually go a lot further towards doing more complete inversions that explain the whole wave field. And we only have really a few examples of data sets that are sufficiently dense to really have a go at that. But
it's really the data rather than the methods.
Maybe. I guess for the methods, I don't know if this is the exactly right answer or not. I agree that kind of doing that style of inversion might give you more complete feeling for uncertainties. We do a lot of other kinds of tests to see how much things move around, and part of that is through this just extensive testing of perturbing all aspects of your starting model and which data are you including and how you parameterize it and all of that. So that's kind of like, I guess, the hard way to do that. But yeah, so I don't know. But maybe we felt like that have comparatively dense data to some other fields. I mean, that Alaska example I showed you is the Aleutian example was sort of the extreme one for being more underdetermined, especially underdetermined. But yeah, I don't know. But it's not something that's been widely done so far. So.
Yeah, Donna, I was curious. What are the constraints on the depth of the hydration zone in the in the plate bending region? Because I know many of the images show the velocities sort of returning to normal mantle velocities towards the bottom of the area imaged, and so that has led people to say, well, maybe there's only 2 or 4 kilometers thick of mantle hydration, but then like our ambient noise tomography in Mariana suggests that you have hydration going like 20 to 25 kilometers below seafloor. So, and that's how deep the earthquakes go also. So are there real constraints from active source, like both yours and Harm's and others, on how deep these hydrated zones go, or is it just something that you lose resolution?
I think that the biggest, so for most data sets, including and most of these kind of dip line velocity models across subduction zones, the answer is no, that we don't constrain the depth. And part of that is, can have observations to look at velocities to greater depths. You need larger source receiver offsets. And unfortunately, subduction zones are super complicated. So if you have like shots that are kind of up over here, going back down through all of this and back to the surface, the arrivals are rattier, or sometimes you don't see turning waves at all from the key part. I think the exception is Harm's model, because they off of Costa Rica, they have a much, this nice long line. And so then I think that Harm would say the data quality here also wasn't brilliant. It's also challenging, but at least you could see larger source receiver offsets and deeper turning waves and have a chance to say something more specific about how deep hydration goes. And I guess for his case, it's more consistent with what you would observe from the passive source side. So I think it's
Well, it's still not nearly as thick as what we observed in Mariana. Mm-hmm. But this is also a younger plate, so
yeah.
And the earthquakes here are also shallower. So.
But I think it's a challenging target for our method because of our need for these long source receiver offsets, and then the complexity of the subduction zone and the challenge of actually recording, getting the arrivals back that we need to see that. So I think this might be the only exception I know of. So.
I guess your vision of towards a more perfect union is sort of the holy grail.
For many people.
But thinking back on the experience from the oil and gas industry, they actually came up with this seismic stratigraphy. It's not really stratigraphy, but you can still do great things. So there seems to indicate that it's really hard to achieve this perfect union. It's more like the United States of America model. There's a federal government, but the different states still have their its own characteristics.
Are the geophysicists like red states and blue states or something? I won't say which one is which. No, it's, there are always going to be challenges. But I guess, for example, in Alaska, we now have these, I think, really cool images and observations of changes in structure. But where I think we're limited in understanding what they mean is by how little we know how it's behaving. So if we could know where exactly in detail near the trench seismicity was, or if and where slow slip was happening, and other things like that, we could get much further towards, and that for that particular problem of connecting properties with behavior. But so the more that we have more stacked data, the better we could do. And so, I could give many other examples. I'll stop there. So we're capable of doing this really detailed and high resolution imaging, and that's really, but we are limited in terms of how deep we can see and the kind of spatial areas we can cover. This is necessarily a pretty focused and detailed approach, so it's strongly complementary to other kinds of seismic imaging, but because of the scale lengths is also very complementary to drilling and geology and many other things. So hopefully you'll be convinced about all that. All right, so there's sort of two broad kinds of active source imaging that we do, and there's many overlaps here, but we can, just for these purposes, there's seismic reflection data. These are, so here we're looking kind of across the bending area of a plate entering the trench and kind of in depth, which is in two-way travel time. And hopefully you can see the seafloor, lots of sediments. They're being offset by different faults. We have this feature here, which is the moho. And so these data are really good at giving us detailed pictures of faults, sediments, magma chambers, and other structures that have a contrast in velocity and density and kind of create a reflection like this. And these are complemented by wide-angle reflection-refraction data, which are normally used to create models of P-wave velocity of the Earth. And so this reflection image is from here, and so now we're looking in depth across the incoming plate. This is colored by P-wave velocity. So all the oranges and yellows are crust. I've changed up the color scale on you. The blues and greens are sediments and water, and then kind of the reds and purples are the upper mantle. And so we can use these sound speed changes to infer changes in composition and things like that. Of course, you can look at reflective boundaries in these and get velocities from these, but these are kind of the two broad categories. So I'll apologize in advance. I'm going to show you a lot of pictures from Alaska because it's my talk, and I love Alaska. It's my favorite subduction zone. But I'll try and have a little diversity and bring in some other subduction zones too. Okay, so before I talk in a little more detail about these two different kinds of seismology, I just want to give you the list of why it's useful to even know anything about these kinds of methods. And basically, they can do a bunch of stuff for us. We can learn a lot about subduction zones using these data. We can have constraints on the overall architecture of the subduction zone, both along the megathrust and beneath the arc to depths of 50 or 60 kilometers. This is getting deeper all the time. I'll show you an example of reflection imaging of the LAB if I get a chance. We can quantify some of the inputs, the thickness of subducting sediment, the incoming plate, how it's deformed at the outer rise, how it may be hydrated. We can look in detail at the properties of the plate boundary, including how wide the cumulative deformation zone might be, changes in pore fluid pressure with depth, and where subducted features are that might be important for controlling behavior. We can understand things about the structure of the overriding plate, including distinguishing different terrains that might be there. And we can also have a kind of a unique view of the composition of the arc crust that can be related to geochemistry. And the list goes on and on. So I'm going to try and show you examples of many of these things once we get a little further down the road. All right, so yeah, what I'm going to try and first do is just kind of go through some really basics of basics about seismic reflection data and wide-angle reflection-refraction data. And I guess the goal of those will be to, if you're not familiar with those, to sort of empower you to look, when you're reading papers about these kinds of data, to understand a little bit more about what they mean and what the limitations are on what's being seen in those data. I'll talk a little bit about how we acquire it, both at sea and on land. And then we'll kind of get in, hopefully spend a lot of the talk really talking about some of the observations that I think are interesting that we're starting to get from these data, particularly on these topics, but maybe some other ones as well. So that is where we're going. All right, so here is a seismic reflection image. It's from Alaska again, and it's across offshore of the Alaska Peninsula. And so I want us to just have a chance to look at this together and understand what's in here. So again, we're looking at sort of two-way travel time and distance from the trench. So here's the seafloor. This is the trench. Contrast, the bigger the reflected energy that you get back. And so we can think of the Earth, which has different sedimentary layerings, different compositions of crust or other things. It's kind of a series of reflection coefficients. And so where 1 is all the energy comes back and 0 is none of it comes back. And basically, we're introducing some seismic source to that, and you're kind of hanging it on each of these little contrast and properties. And basically, that's each trace of our 30,000 traces in our seismic reflection image. Okay, and so if we now kind of come back to this image again, you'll see in many papers about seismic reflection data, and in this image here, that we're kind of looking down on the Earth in depth, but we're actually looking at two-way travel time, because that's what we measured. So the time it took that seismic wave to go down and come back up. And so, which is of course related to how deep some boundary in the Earth is and the velocity. But if we had done the experiment in this very simple way that I've kind of asked you to understand this image of just going down with one receiver and one source and just firing our source and recording our arrivals and doing that 30,000 times along this line, we would have no idea what this velocity is. There'd be a perfect trade-off of how deep it was to some layer and what the velocities are in the overriding plate. So the way that we actually collect these is not just with one source and one receiver, but with many receivers over a range of distances between our source and our receiver. So here is a seismic ship cruising along, in this case with a source and some streamer. And now you have all these different bounce points of seismic waves off of some layer in the Earth. And so by having many receivers, multi-channel seismic data, for any little given point on the Earth, we've hopefully had a bunch of different reflections off of it at different source-receiver offsets. And as we'll talk about, that's useful for telling us not only so that we can constrain the velocity of the mediums through which these rays are traveling. But it also helps us beat down the noise, because now, instead of just having one source and one receiver, we're recording many reflections. All right, thank you. You are very welcome to download whatever you wish during my lecture. I won't be offended at all. Not that you needed my permission. All right, we're going to switch gears a little bit from mantle isotopes and move into the world of active source seismology, which for all of its benefits may not be able to show us where EM1 is and what it is, but it does have many uses, as I hope you'll see. So I hope you had a lot of coffee at the break, because I want to show you a lot of stuff that I think we can learn about subduction zones using this type of seismology. All right, so I think that Doug and Brandon have given you great introductions to general principles about seismology and told you about the wide spectrum of passive seismic imaging techniques that are out there. And so today I'm going to focus on active source seismology. And the thing that really makes this special is that not only do we control where we put our receivers for sound waves, but we can also control our source, how big it is, where it is, when it is. And so this means that we have sort of a unique ability to do a higher resolution of imaging of the Earth than is possible with some other types of methods. And so, and we can really optimize depending on what we want to see. And so I have my terrible cartoon up here of a marine experiment where we're creating sound waves with an air gun source, and we can record those on streamers or on other autonomous seismometers. So we'll talk more about that. But just to kind of whet your appetite for the kind of constraints we can have, we can look at the Earth in kind of this kind of detail. So, I didn't put a scale bar here, but this is about 1 kilometer, and this plot is shown at a vertical exaggeration of 2 to 1. But you can see detailed sedimentary layering, thrust faults, and other structures. And we can also get really detailed constraints on seismic wave speeds in the Earth. And so that's being shown here with the colors behind this image, where reds and warm colors are slower, and blues are faster, but hopefully you can see there's like a nice low velocity zone here within this, this area along the subducting plate boundary. So we'll talk about all of this in more detail. And hopefully, looking at this image, you can see some other, this bright reflective stuff. A lot of that is sediments above the crust. But hopefully, even in this unadorned seismic image, you can see some other stuff too, particularly this and this. And this is actually, these are reflections off of the plate boundary to depths of, this is about the equivalent of 50 kilometers or something like that. And so when we look at this image, we can kind of think of this as, you know, it's common for us to do all these nice things to visualize the data, like make it all pretty and colored. But basically what this image is 30,000 individual wiggle traces. So it's as if you kind of cruised along on the seafloor with one source and one receiver, and you set off your source, and you recorded some seismic wave that went straight down and came straight back up. And so it went straight down and bounced off of things in the earth and came straight back up. So if we kind of zoom in on one of the 30,000 traces in this image, it would look kind of like this. So you have these sort of positive and negative swings. And the amplitude of these arrivals is related, as we'll see, to the contrast and properties that are in the Earth. But in this image, we're kind of coloring in the negatives are red and the positives are black, just to be able to see things a little bit better. And so our seismic waves go down, they bounce off of things in the Earth, and they come back. And the thing that controls the amount of energy that comes back and the amplitude of those reflections are contrast and properties within the Earth, contrast in velocity and density. And so if we have some P wave that comes down and encounters a contrast in properties, which we're going to express as impedance, the amount of energy that comes back as a P wave or an S wave or is transmitted as a P and an S wave depends on the contrast and properties here and the angle at which it strikes this interface. And so for the most simple case of just a sound wave going straight down, hitting an interface, and straight back, we can consider how much of that is reflected or transmitted as all in terms of this contrast and velocity and density of the layer above that interface and the layer below it. But hopefully you can see the bigger the